of maximal ideal. In my earlier video I had seen phi be a mapping from R to R dash who is be ring homomorphism and S equal to image of this phi which contain R dash, then obviously S is a subring, and by first isomorphism theorem we can tell R mod car phi is isomorphic to S. And this theorem we all of us know. I have seen this theorem in V4 and I have seen the correspondence theorem. By correspondence theorem we can tell easily there exists a bijective correspondence ideal in R containing car phi to ideal in the image S. That means there exists a mapping which is bijective between ideal in R containing car phi and ideal in S. The picture is look like, let phi be a mapping from R to R dash, and this mapping is obviously epimorphism. Epimorphism means we all of us know ring homomorphism and onto. Then at first see the picture. This is R and this is R dash. There exists a bisective correspondence between the ideal of R that contain the car F. That means here the car F contain in I dash to ideal of R dash. Consider this ideal as I double dash. Means I double dash be the set of ideals of R dash and I dash be the set of ideal that containing kernel of F. Okay, are you getting? And by correspondence theorem we can tell if we take any ideal from I double dash, then there exists always an ideal in I dash that containing kernel of F. And I have discussed correspondence theorem because to find maximal ideal this theorem is very important. Just see one example. At first we all of us know R is a ring and an ideal I is maximal if and only if R mod I is a field. Okay. Also I had seen in my earlier video Rx modulo ideal generated by x square plus 1 is isomorphic to C, and since C is a field then obviously this ideal be maximal ideal in Rx. And the proof is look like, just recall, consider a mapping phi from Rx to complex number such that f of x equal to f of I. This is obviously ring homomorphism, and kernel of f equal to f belongs to Rx such that f of I equal to 0. Who is this equal to actually x square ideal generated by x square plus 1. We all of us know this part in earlier video. And obviously this mapping is onto, because if we consider an arbitrary element a plus ib from the complex number C, then phi of a plus xb would be a plus ib and ab belongs to real number. That means the ring Rx modulo F means here ideal generated by x square plus 1 is isomorphic to complex number. Also we can tell this by correspondence theorem. There exists a mapping from Rx to complex number. Then by correspondence theorem we can say ideal in Rx containing x square plus 1 to there exists a bijection between ideal of C. And since C is a field, so obviously there exists two ideal, 0 ideal and C itself. Therefore, From this we can conclude the only ideal in Rx that containing the ideal x square plus 1, because here the kernel of f equal to ideal generated x square plus 1 are only x square plus 1 and the whole ring Rx. That means if we can write x square plus 1 contain Rx, then I is either x square plus 1 or I is either Rx. And by this situation, we can tell ideal generated by x square plus 1 is a maximal ideal. Okay? Now my next question is, determine the ideal of the ring R Ct modulo T square plus 1. This type of question is very important for any competitive exam. For this, consider the ring homomorphism phi from Ct to R, where the ring R is denoted as Ct mod T square plus 1. Here the function is denoted as Ft maps to Ft bar, where T bar equal to just coset of the element T plus T square plus 1. Are you getting? Because here the ring consider it as Ct mod T square plus 1. Okay? Obviously this mapping is onto and kernel phi equal to, just think, T square plus 1. Just I leave it for your exercise. This is easy method. Here T square plus 1 maps to T bar square plus 1, which is actually equal to 0 bar in the ring Ct modulo T square plus 1. This is the actual method. Okay? Now I will use the correspondence theorem. Correspondence theorem imply ideal of the ring R imply ideal of Ct that contain the ideal T square plus 1. That means we have to find or ideal of Ct that contain T square plus 1. Let I be an ideal of Ct containing T square plus 1. Obviously Ct and T square plus 1 be one ideal, but there exist also other ideal. Let I be an ideal of Ct containing T square plus 1. Consider I equal to ideal generated by Ft, where for some Ft belongs to Ct. Okay? Because at first we have to find the ideals of Ct that contain T square plus 1. Means obviously T square plus 1 belongs to ideal I, and by the definition of ideal we can write T square plus 1 equal to Ft times Ct, and from this line we can tell easily Ft divide T square plus 1, and here the definition of ideal Gt belongs to Ct. Okay? Therefore, actually we want to find such polynomial Ft that divide T square plus 1. When if we consider f equal to 1, then 1 times T square plus 1 equal to T square plus 1. That means 1 obviously contained in the ideal t square plus 1 and 1 equal to actual the whole ring Ct. Other, if we choose f equal to t square plus 1, then t square plus 1 times 1 equal to t square plus 1, then t square plus 1 obviously contained in t square plus 1. This is obviously always true. Whole ring and t square plus 1 obviously contained in t square plus 1. Now, if we consider t plus I, then t minus I times t plus I equal to t square plus 1. That means t square plus 1 contained in t plus I. T square plus t plus I. From this line, similarly we can choose also f equal to t minus I. Since t minus I times t plus I equal to t square plus 1, then obviously by this, similar to this, we can tell t plus I contained in t square plus 1 contained in the ideal t plus I. That means there exists 4 possibility. Ideal of Ct containing t square plus 1. One possibility whole ring, other t square plus 1 itself, other t plus I, and other possibility is, here t minus I. That means there exists 4 ideal in the ring R. R means here Ct modulo t square plus 1. These are 0 ideal, ring itself, t bar minus I and t bar plus I in R. And 0 ideal actually corresponds to t square plus 1. This is the smallest ideal, and the whole R corresponds to Ct, and t bar minus I corresponds to t minus I, and t bar plus I corresponds to t plus I in the ring Ct. Are you getting the idea? Well, means this ring has 4 ideal. 1 0 bar, 1 the whole ring R, 1 t bar minus I, and other t bar plus I. Now, I will see one question of CSIR NET 2014, which is actually use of correspondence theorem. Let PQ be distinct prime, then option 1 Z mod P square QZ has exactly 3 distinct ideals. Option 2 Z mod P square QZ has exactly 3 distinct prime ideals. And option 3 Z mod P square QZ has exactly 2 distinct prime ideal. And option 4 Z mod P square QZ has unique maximal ideals. Actually, the ring Z mod P square QZ is isomorphic to Z P square Q. This is because if we consider the mapping f from Z to Z P square Q such that f of n equal to class of n, then obviously this mapping is ring homomorphism and kernel of f equal to P square QZ. Then by first ring isomorphism theorem, we can tell Z mod P square QZ is actually isomorphic to Z mod P square Q. Means, since in the question we have to find the ideal of Z mod P square QZ, therefore, by correspondence theorem, we can tell easily actually we have to find the ideal which is containing p square qz in Z for this mapping. Are you getting the idea? Why the correspondence theorem is very important to find ideal? Well, and as same like the ring Ct mod t square plus 1, this ideal actually would be, here the ideal containing the kernel of f p square qz in Z means same like before, the all divisor of p square qz, that means ideal generated by p, ideal generated by q, ideal generated by p square, ideal generated by pq, ideal generated by p square q and Z. Are you getting? These are the total ideal in the ring Z mod p square qz. This is actually same as the zero ideal, which be the smallest ideal, and same like Zn, we all of us know the ideal of Zn are look like NZ types, okay, and the maximal ideal of Zn are when only the n is prime number, because if we consider 4z, then 4z obviously containing 2z. Similarly, if we consider 6z, then 6z containing 3z and also 2z. So only when n be prime number, then in Z those n are maximal ideal, same like prime ideal. Similar to Zn, here since p and q are prime number, so ideal generated by p and ideal generated by q be the maximal ideal of this ring. If we consider p square, then the ideal p square is contain ideal p, so this is not maximal ideal. Are you getting the idea? Okay. Notice the ring has 1, 2, 3, 4, 5, 6 ideal, and in this ideal only 2 ideal are maximal. So that means option 1 is a wrong option. Z mod p square qz here indicate 3 distinct ideal, but Z mod p square qz has exactly 6 distinct ideal. So obviously option 1 is a wrong option. And option 2 indicate Z mod p square qz has exactly 3 distinct prime ideals. This is also wrong option. And option 3 is the right option. Here has indicate Z mod p square qz has exactly 2 distinct prime ideal. This is right option. And 4 option is also wrong option. Z mod p square qz has unique maximal ideal. This is also wrong option. Next question is, let Z125 be the ring of integer of modulo 125 under the operation addition modulo 125 and multiplication modulo 125. What is the number m plus n would be? Similar to before, Z125 means actually the 125 equal to 5q. Actually this is the all divisor of 5q would be. This is ideal generated by 1, ideal generated by 5, ideal generated by 5 square and ideal generated by 5q, and this is actually the 0 ideal, and ideal generated by 1 is actually same as Z125, and in this ideal only ideal generated by 5 is a prime and maximal ideal. Okay? We all of us know number of units of Z125 is denoted as 125, which is actually equal to 5 cube. This is same as 5 cube minus 5 square, which will equal to 125 minus 100. That means this value would be, sorry, here 25, then means this value would be 100. That means number of non-units which is denoted as n, this would be 125 minus 100, which is equal to 25. That means the value of m plus n equal to, where m be the maximal ideal, here only one maximal ideal, and n be the number of non-units, here 25 non-units. That means this value would be 26.